Hello, everyone. Welcome to the Temporal Graph Reading Group this week. Um, we are very glad to host our very own Julia, who will be presenting her recent work, History Repeats Itself, a baseline for temporal knowledge graph forecasting. And more background on Julia. Julia is a research scientist at NEC Labs Europe and a PhD student at Mannheim University, supervised by Professor Heiner Sturkenschmidt. Um, Currently, she is doing a research internship at Mila. Her research focus on graph-based machine learning, and she's interested in how to incorporate the time aspect in knowledge graph representations. And prior to joining the NEC Labs, Julia graduated with a master's degree from the Stuttgart University, where she studied engineering, cybernetics, with a focus on autonomous systems and control theory. Yeah, I will hand it back to you, Julia.
Thanks for the introduction and thanks for coming. So I'm going to present our paper, History Repeats Itself, a baseline for temporal knowledge graph forecasting. This was a collaboration between NEC Labs Europe and University of Mannheim and done together with Christian, Federico, Timo, Annette, and Heiner. All right, and if you have any questions, feel free to interrupt me anytime. Okay, so probably most of you know this, but we are talking here about temporal knowledge graph forecasting. So we want to predict links in knowledge graphs for future time steps based on the history of knowledge graphs. And in our case, this history of knowledge graphs is represented as graph snapshots, where each snapshot contains all the quadruples that are known to be true at this time step. And we want to predict for the future which are going to be the links in this graph. There is quite some related work on temporal knowledge graph forecasting. I'm just going to give a brief overview. So we have some work on deep graph networks. We have some work which use reinforcement learning. We have some rule-based approaches who also combine maybe some other approaches and some other contributions which cannot be placed in the above categories. And then there has been some unified evaluation protocol represented to evaluate all of them. What has been missing so far is, however, a comparison with just some simple baselines to somewhat grasp if we are really making progress in the field or not so much. And this is now where our work or our contribution comes into place. We introduce a novel baseline for temporal knowledge graph forecasting, we introduce 3 variants, a strict and a relaxed recurrency and a combination of both. And it's a rather simple approach. We only have those 2 hyperparameters and no training phase. What we found is that we get some surprisingly good empirical results. And we also show a failure analysis and do a detailed comparison of the prediction of the baseline to other methods predictions. And yeah, this is exactly what I'm going to talk about in this presentation. So I will explain the baseline, I will show the experimental setup and results, and that's about it. So before we start, a few preliminaries. A temporal knowledge graph is a set of quadruples. So you typically have subject, relation, objects, and timestamps. And yeah, you have a set of entities, you have a set of possible relations, and a set of timestamps. We have this running example to somewhat visualize this a bit better. So this is a very simple, very small temporal knowledge graph, which lists in a simplified way the clubs that Marta Vieira da Silva, or known as Marta, played for from 2001 to 2009. So you have the subject, the relation, the objects, and the timestamps. And now if we do temporal knowledge graph forecasting, we want to predict quadruples for future time steps, D plus, given a history of quadruples. In this work, we focus on entity forecasting, so we want to predict either an object or a subject for the given queries. In our running example, when we now suppose it's time step 9, we want to predict, for example, for time step 10, which club Marta will be playing for. Similar like for knowledge graph completion in static setting, this is approached as a ranking task. So for a given query, the methods rank all the entities in the set of entities using the scoring function and assign some plausibility scores to each quadruple. And in our work, we design several variants of a very simple scoring function that assigns a score to a quadruple at a future time step given a temporal knowledge graph. And as I said, we have 3 variants of this recurrency baseline, and now I'm going to step through them step by step. So for the strict recurrency baseline, the questions that is asked is, has the triple that we want to predict at a time step t plus already been observed before? So the simplest way of approaching this is, okay, we assign a score of 1 if this triple has been seen before and a score of 0 otherwise. So in our running example, this would mean we assign a score of 1 to all the clubs that Marta has been played before. However, this does not take into account time, and we want to take into account time. So we introduce this time weighting function, delta, which is a very generic function. It takes the query time step and the previous time step k in the graph, and then assigns a value based on this time weighting function. So if we would, for example, use this linear function k over t plus, we would get t-scores, which would then assign the highest score to the club that Marta played for most recently, which somewhat makes sense because it's, if you don't know anything else about Marta, you would probably assume she still plays for the most recent club. However, it could also be that we have triples with slightly different characteristics. So let's now assume we extend our example with these other clubs, or we have those football clubs, soccer clubs that win the Bundesliga, which is a German soccer tournament. And now we want to predict which club will win the Bundesliga in the next time step. Instead of just saying, well, the same as last year, we would probably do something more like, yeah, the club that wins most times will win the Bundesliga again. And that's why we extend our scoring function to also take into account the frequency of wins. So now for if we still use the same time weighting function, but also take into account the frequency of wins, we get these kind of scores for the different clubs. And we would assign the highest scores to clubs that won basically most often and most frequently. Somewhat simple. And now we can parameterize delta, the time weighting function. And for example, we can set delta to 2 to the power of lambda times k minus t plus. And lambda is in our case a hyperparameter. And depending on how we set this lambda, we have different kind of time decays. If we set it to 0, we have no time decay. If we set it to 1, it becomes very steep, and so on and so on.
Just a quick question. Can you go back to the previous slide for the frequency?
Yep.
Frequency, so what are you exactly computing here? So you are taking the number of times the edges do show up divided by the total number of timestamps so far?
Yes, a bit more sophisticated. So this is when does this edge show up? And then we put this in this time decay function. And here we have all the time steps also in the time decay function.
Oh, okay.
That's kind of a combination of both.
Okay. So you would wait basically if you win just now a lot more than if you win 3 years ago.
Yes, exactly.
I think some audience have difficulty seeing the shared screen. Do you want to just try like reshare the screen and see?
Yes, I will stop share and try it again.
But yeah, just try share again. Okay.
What about now?
See the slides from my end.
I'm starting the speaker mode.
See the slides now. Okay.
Still all black.
Okay.
Another person sees them. Okay. Okay, it seems like most people can see them.
Okay, so we'll continue with the talk now.
Thanks for the feedback.
No problem.
Did this answer your question, Andy?
Yes. Yes. So I think this time weighting thing is interesting. But you are also making some very explicit assumptions here. You assume that winning recently is a stronger bias. I mean, that's the common assumption. However, that doesn't necessarily mean that you will likely to win often in a row.
Yeah, we're not really taking into account winning in a row, just how often and how recent. Yeah. However, now if you set this lambda, so we have this time weighting function 2 to the power of lambda. And depending on how we set lambda, we have this different kind of time decay. We have some different properties. So I think this also kind of answers your question. This is some theoretical stuff we have in the paper, but the main two summaries of this are: we do not need to search for an optimal time weighting function if we choose it to be strictly monotonically increasing with respect to k, which is somewhat convenient. And the second one, which refers to your question also, is that different values of lambda reside in a scoring function, which is situated between c and phi and psi delta lambda. So if we, for example, set lambda to 0, the time decay is very flat and it's more of a frequency-based approach. If we set it to 1, it's very steep and it's just a recency-based approach. And depending on what kind of relation you have, we can set a different lambda and you have kind of a different behavior, which kind of models everything in between.
I see.
Yeah.
Wait, so you have this parameter for each relation type?
Yes, exactly. That's the next slide. We select a different lambda for each relation type. So if we have one relation type which is placed for, we assume that all triples or quadruples have like a same behavior, similar behavior. And if we have another relation like wins, we can select another lambda. And we select this value of lambda just based on the validation MRR. So we do some kind of grid search. We have 14 values, 14 potential values of lambda, and we just do a grid search on the validation MRR.
Do you think having a learnable function here will make it even perform better? Like
Probably.
NLP, which learns the frequency of the wave function, the time.
Yeah, we were thinking about it, but it would probably make it too complicated, given that it already performs kind of good, and the nuances in between are probably not that much increasing performance. So for the sake of simplicity, we just did a grid search, but yeah, might be worth a shot.
Okay, thanks.
Thanks for the question. Okay, so now we have the strict recurrency baseline. Now, just imagine that we have a new player in our temporal knowledge graph. The player appears for the first time. We can no longer use the strict recurrency baseline because we will never have a quadruple that has been appeared previously or a triple. So what we do is we have this relaxed version where we say how often have parts of the triple been observed in the data. So for a query, we compute a normalized frequency that the object has been in a relationship with any kind of subject. To make it a bit more graspable, we have this example. We have the new player, Aitana Bonmati, and we want to see which club she will play for. We don't know anything about her. We only know the clubs that people have played for. And we will just keep it very simple and assign the highest score to the club that most people or triples have played for it, most time steps have been in. So in this case, we would just say, okay, I guess she plays for Umia IK because most people play for that. It's very simple, not very sophisticated. We wanted to just keep it simple to take into account this possibility that we don't know anything. We do not have any time decay here. So yeah, because this is very simple, because we keep it very simple, we are mainly interested in combining this relaxed recurrency baseline with the strict recurrency baseline. And we expect it to fill gaps if we don't know anything else, and to resolve ties in case we have some ties from the strict recurrency baseline. And now we already come to the third way, which is the combined recurrency baseline. As the name suggests, it's just a combination of the two baselines. And we have it again rather simple. It's just a linear combination where we say alpha times the strict one plus 1 minus alpha times the relaxed one. And alpha is a combination weight. It's again a kind of hyperparameter. We select one alpha per relation, and we again do just some grid search on the validation MRR. So hyperparameters, as I said, we have this lambda, the time decay, and we have the alpha, the combination weight. And we select the values of both per relation based on the performance of the validation set. So this is just a summary. I think you know it by now. We have the strict one. Has the triple occurred before? And how often have parts of the triple been observed in the data? And we combine it. So now I want to talk about the experimental setup. We follow an evaluation protocol that we have defined in the previous work. And we use the MRR and the hits at 1 and hits at 10. We do a time-aware filter setting, and we do single-step prediction. So we predict one step into the future, and then feed the ground truth and predict another step. I want to talk a bit about data sets. We use those 5 data sets. They're commonly used in related works. And we compute some additional statistics, namely the recurrency degree, which is the fraction of test temporal triplets for which there basically would have been in the graph before. So this is this value, and it's somewhat an upper bound of the strict recurrency baseline's performance. Because if the triple has not been observed before, then the strict recurrency baseline cannot do anything. And the direct recurrency degree is the fraction of the test temporal triples which have been in the graph in the previous time step. From our baseline's perspective, these are the test triples that have a somewhat trivial solution. And what you can see here is that for Yago and for Wiki, we have very high values for both the direct recurrency degree and the recurrency degree. So when just looking at this table, we expect the baselines to perform very well on these data sets. So now some experimental results. First, we just look at the relaxed, strict, and combined with MRR and hits at 10. And what do we see? First, that the combined recurrency baseline is mostly better than the strict and the relaxed one. Also, we see that the strict recurrency baseline by itself is not much worse. And the relaxed one just gives us minor improvements. This also, says what we were expecting, because it's just here to fill gaps to resolve ties. And now if we compare to related work, we compare to all those methods. Also these results reflect somewhat the values for the recurrency degree, because for the datasets Yago and Wiki, we have very, very high MRRs, and these are also the ones with the high recurrency degrees. Okay, now if we compare to related work, what do we see? We see that we have with the baseline the highest scores and both for 2 out of 5 datasets for GDAT and for Yago, and the third highest score for the Wiki dataset, which indicates that most models seem unable to learn and consistently apply this very simple recurrency forecasting strategy. And then for IS14 and IS18, the majority of related work has better results, which indicates that there are more complex dependencies that need to be captured for these data sets, which these baselines cannot capture. So what we find is basically that none of the methods proposed so far can accomplish the results achieved by this very simple combination of the baselines for 2 out of 5 data sets. And this is somewhat surprising and raises some kind of doubts about the predictive quality of those current methods, at least on these data sets. And yeah, we have this visualization. And now we wanted to look a bit more deeply on what's happening there, or what are the problems that the other methods might have. And that's why we chose the Yago dataset, and we picked the 4 best related work methods and the baseline, and we compared it on a per relation basis. So what you see in this figure is the different relations that we have in the Yago dataset. The MRR on the y-axis, higher is better, the different related work methods, and then in color, the recurrency baseline. And for pink means it occurred very often in the test set, this relation, and red means it didn't. What do we see? First one is that we have some kind of categories for the MRR here. Either we have very high MRR, nearly 100, for example, or very low MRR, below 20. For all relations, we see that the recurrency baseline has the highest MRRs. seems that the capabilities of related work, like taking into account multi-hops, taking into account different relations, and so on, do not seem to be beneficial here in this data set. And also, due to this rather limited information that we have in the data set, just this limited amount of relations, it does not seem to be feasible to reliably predict prize winners or graduation details or even deaths of people. So for this data set, because it's already very good, the prediction on the easy relations, and these seem to be not so feasible, we expect no significant improvement in future work on Yago data set. However, we say that you can still use it to do some kind of sanity check for methods. Like, is the method able to find at least the simple recurrency? And all related work somewhat fail for some relation. And we can see that the main disparity in the overall MRR is for two relations. One, the place for relation, and one is affiliated to relation. And queries attributed to these relations are almost 50% of the test queries. And when we look at it in this detail, we can somewhat find the specific weaknesses of each method, which is just possible because we compare it by this baseline. We can now see, okay, what would be possible if the method can do this easy recurrency thing, and which method fails where. For example, we see that time traveler is fine with those, but it's somewhat having a problem with this is affiliated to relation in head direction. And then CEN and REGCN, they are fine with is affiliated to, but they have some problems with their place for relation. So when one does this, it's somewhat nice because one can do some targeted or more targeted improvements. We also, in addition to this peer relation analysis, did a failure analysis where we just looked at some example queries where we think that the recurrency principle offers an ambiguous solution. And we again use the Yago data set because we here have this very high direct recurrency. And now for each model, for each of those models that we just showed, we count for how many queries the following conditions are fulfilled. So we have the test query with the correct answer O. It must be fulfilled that O, or this test query, was in the graph in a previous time step, that the model proposed another O star, which is not O as top candidate, and that this O prime is not in the graph before. So it proposed something which is somewhat wrong. And we do the same for the head queries. And then for each model, we just randomly select some queries and describe the mistakes made. This is not a complete kind of evaluation. It's just looking at some examples to understand what's going wrong. And what do we find for time traveler? We see that some of its top candidates belong to an incompatible type with respect to domain and range. For example, for this query, who plays for years SK, it predicts Spain national U23, where it should predict a person. Or for this, who plays for Derby County FC, it says baseball ground, which is not really reasonable at all. So time traveler seems to have some problem with taking into account or with predicting the correct type. Then Xerdi has a different problem. It tends to predict in many of those cases a candidate as a subject or an object when the same was given as an object or subject. So it does this kind of symmetrical predictions where it says John is married to John. And the same issue has basically been found a few years back in static non-temporal knowledge graph completion methods. So it seems to be an issue that methods can have. And then for CEN and REGCN, we have errors for the place for relation, mostly in tail prediction. The types are correct. We cannot find any systematic error pattern. We just assume that for some reason, both models are not able to learn that this place for follows this simple regularity of strict recurrency. Yeah, so by looking at this more in detail, we find some insights for each of the analyzed methods and their current weaknesses. And this could now lead to future work to applying these insights to improve these models, to no longer have these weaknesses. And we argue that by looking or comparing with these baseline results, it's somewhat easier to find the problems, because otherwise an MRR of 70 would look good enough, probably. Okay, so to conclude, we introduced this baseline, which employs the concept of facts recurrency by having the strict recurrency, the relaxed recurrency, and a combination of both. We find that it is a better or competitive alternative to existing models on 3 out of 5 datasets, even though it's not able to grasp any complex dependencies, and this is somewhat surprising. And we hope that with this work, we can stress the importance of baseline. So if a model fails when a baseline succeeds, it should probably be subject to critical scrutiny. And then we did this analysis where we looked at existing models and tried to find the limitations. And yeah, the code is available on GitHub. Here's the QR code. Here is the link. And that's all from my side.
Yeah, thanks for the nice presentation here. Feel free to post like any questions in the chat or unmute yourself. Yeah, I do have some questions, but I've been asking a lot of questions, so I don't know. So if like any of you want to ask questions first, feel free to. Otherwise, like I'm curious how much transferability you think. Oh, we do have a question from the chat. I will continue my question later. So, is it possible to adapt this work to temporal graphs where we have standard triple of source, destination, and time instead of a quadruple with the relation type as in temporal knowledge graphs?
Yes, I think it is. It would then be very similar to, do you know EdgeBank, which is a baseline for temporal graphs, and it would then be somewhat an extension to EdgeBank because it would take into account this time decay. But yes, you could, instead of having this dictionary where you have the previous subject relations and object, just have the previous subject and object. Just the relaxed recurrency baseline would no longer really work because it takes always into account who has been mostly with that relation. So instead of that, you would just say, okay, the most frequent object.
That's basically PopTrack, I think. That's basically the PopTrack paper where they count the most frequent destinations. So,
yeah.
So actually both variation of ideas have been tried in standard temporal. Yeah.
Yeah.
PopTrack, yeah, exactly. You can find this in last year's temporal graph learning workshops, like proceedings. But yeah, so I think the idea is very interesting. I think the second, the relaxed one, I think it's basically a code start problem. So if you have a new user or a new entity enters the graph, you have no information about that particular entity. What do you do to make predictions, right? So basically what you're doing right now is like, if the most popular Netflix movie is, I don't know, like Love Actually or something, and then when a new user comes, you always recommend this movie to that person, right? That's basically what that baseline does, right?
Exactly. For example, it's somewhat nice to use it here in this died-in relation because you don't know where a person will die in, especially because you don't have any other information about this person. But you just say basically the people are gonna die where most people die. And it gives an okay-ish MRR as compared to the other methods. So nice.
Yeah. Yeah, but I guess what I was thinking about taking this idea further is you can also do rapid adaptation based on basically when you observe zero information, of course you cannot make any, strong guesses. But as soon as you start to like observe one or two edges from this new user, then you can adapt it to something that are closest to whatever you observe. Like so I don't think like either the baseline that you propose does something like that. So like for example, if you have a new soccer player, right, and then this player plays for team A and then team B, that's what you just observed, and then you also have in your data set another player that played for A, B, and then C. So then you can use that information to predict for C.
Yeah, you're right. That would go a bit in this rule-based direction, where you would learn if a person plays for A, then goes to B, it then goes to C. That's true.
Yeah. Yes. Yes, exactly. Yeah. Okay. Sounds good. Feel free to type more questions in the chat. And thanks for the nice presentation, Julia. Yeah. Yeah. So I think if there's no more questions, then we can like wrap up here for today. And yeah. So thanks for coming to the reading group. Oh, for next week we are skipping the reading group because of the NeurIPS deadline. So there will not be a reading group next week. So we'll see you 2 weeks from now, I think. Yeah. Okay. Have a nice
Thank
day.
you for coming.
Thank
Thanks.
you.
Bye.
Thank you. See you.